The future of quantum computing in AI, what's coming next? For decades, the story of computing has been one of exponential progress. Each generation of machines smaller, faster, and more capable than the last. But even Moore's law has its limits, and the conventional transistor is approaching the end of its physical runway. Enter quantum computing, a paradigm so radically different that it promises not just faster computation, but an entirely new way of thinking about information itself. And when quantum computing meets artificial intelligence, we are no longer talking about incremental change. We're talking about a revolution that could reshape science, industry, and even the limits of what machines can learn. To understand where this convergence is heading, we first need to understand why quantum computing is so transformative. Traditional computers, no matter how powerful, rely on binary bits, ones and zeros, to represent information. Quantum computers, however, use qubits, which can exist as both 1 and 0 simultaneously thanks to the quantum property known as superposition. When multiple qubits are entangled, they can process a massive number of possibilities at once, exponentially increasing computing power for certain types of problems. Now, imagine applying this principle to AI models that must sift through astronomical amounts of data or optimize across billions of variables. Machine learning today is largely constrained by computational limits: how long it takes to train models, how much energy they consume, and how efficiently they can explore complex mathematical landscapes. Quantum computing doesn't just accelerate this, it rewrites the equation entirely. In the coming decade, quantum computing's influence on AI will unfold in several phases. The early phase, which we are living through now, is all about hybridization. Companies like IBM, Google, and IonQ are pioneering quantum classical hybrid systems where quantum processors work alongside GPUs and CPUs to tackle subproblems that are too complex for classical hardware alone. These hybrids are already being used to speed up optimization problems, like finding the best neural network parameters or simulating the physics of materials that could lead to new AI chips. But this is just the beginning. The real breakthrough will come when quantum advantage, when quantum computers outperform classical ones at meaningful tasks, becomes consistent and scalable. Once that threshold is crossed, the very structure of AI architectures could change. Instead of today's deep learning models, which rely on layers of weighted neurons, we could see quantum neural networks, where information is encoded in quantum states and learning happens through manipulation of probability amplitudes rather than weights. These quantum neural networks could process data in ways that classical networks simply cannot. For example, quantum systems can inherently represent and compute with uncertainty, which is a core aspect of intelligent reasoning. This means quantum AI might naturally excel at problems that require understanding ambiguous data, such as human language, biological systems, or global economic simulations. Instead of brute forcing through massive datasets, quantum AI could explore an entire landscape of possibilities simultaneously, identifying optimal solutions with far fewer steps. One of the most promising areas is quantum machine learning, QML, where algorithms are designed to run natively on quantum hardware. Quantum versions of key AI algorithms like support vector machines, clustering, and linear regression are already being developed and tested on small-scale quantum systems. Early results suggest that for certain datasets, QML could achieve exponential speedups compared to classical methods. The implications stretch far beyond faster training times. Quantum computing could enable AI to simulate phenomena that were previously impossible, like molecular interactions at atomic precision or the behavior of complex ecosystems. Imagine AI-powered drug discovery where quantum simulations of protein folding are integrated with machine learning models that predict viable compounds in real time. Or AI-designed materials where quantum computers explore the properties of millions of molecular configurations at once, finding perfect combinations for superconductors, batteries, or quantum sensors. Energy efficiency is another frontier. Training large AI models today consumes vast amounts of electricity, sometimes more than small countries. Quantum processors operating at the atomic level could drastically reduce that consumption for certain types of computations. The synergy between quantum and AI might finally break the energy bottleneck that has limited the scalability of current deep learning. However, this future is not without challenges. Quantum hardware is still fragile. Qubits are extremely sensitive to environmental noise, requiring cryogenic temperatures and sophisticated error correction. Most quantum systems today operate with only dozens or hundreds of qubits, far below the millions that may be required for general-purpose quantum AI. Moreover, quantum programming itself is complex, requiring entirely new languages, algorithms, and intuitions about computation. In parallel, AI researchers are preparing for this quantum leap. Open-source frameworks like TensorFlow Quantum and PennyLane are allowing developers to begin experimenting with hybrid quantum AI systems. These early-stage efforts are not about immediate utility. They're about building the foundations of a new computational paradigm. The developers who learn to code in the quantum AI ecosystem today will be the pioneers of tomorrow's intelligent machines. And that's where the most fascinating philosophical questions arise. If classical AI represents the digitization of thought, quantum AI could represent the quantization of thought itself, a model of intelligence that doesn't just mimic the brain but may share its probabilistic, non-deterministic essence. Human cognition, after all, is not strictly binary. It thrives on ambiguity, inference, and intuition, all qualities that quantum systems naturally embody. The industries most likely to be disrupted first are finance, logistics, and pharmaceuticals, domains that rely heavily on optimization and prediction. But the deeper transformation will come when quantum AI becomes accessible as a service, much like cloud computing did a decade ago. Once quantum computation is integrated into everyday AI workflows, innovation will accelerate at a scale humanity has never experienced before. So what's coming next? The short answer, everything. The quantum AI revolution won't arrive all at once. It will unfold in waves. The first wave will make AI faster and more efficient. The second will make it smarter, more intuitive, and capable of solving problems previously deemed impossible. And the third wave, the one that will redefine human civilization, will blur the line between artificial and natural intelligence altogether. The next generation of computing won't just think faster, it will think differently. Quantum AI is coming, and it promises to expand not only the boundaries of machine intelligence, but perhaps the very definition of what intelligence means.